It was an oddly quiet recording in progress. Okay. All right. You're free to join this class remotely if you want. I don't take attendance here, so if you can't come to class for any reason, you can use the Zoom link. The lectures are also recorded here, so if you miss class, you can also view them online. Office hours every day are just right after class. So if you have questions or you just want to talk to me about something, I'm available for like an hour after class every time after lecture. All right. So what we're going to be doing over the course of the semester is we're going to learn how to manage big data. And there are ways that larger scale data is fundamentally different from other maybe data set sizes that you might have in mind. I know that, especially in the technology space, we have data set sizes that are just far larger than many, many other fields. Like, my sister works in ecology and she spent an entire summer gathering 100 different data points for turtle populations in New England. And that's not what we're going to be doing here. You know, I work at Count just down the street, and we do like e-commerce fraud work, and we have billions of transactions in our data sets. And so these are the types of things that you're going to learn to manage over the course of the semester. And so what we're going to do is we're going to understand how these methods and these algorithms differ from normal analysis types. Specifically, we're going to be using a tool called Spark, which is this distributed data analytics platform that we can use. And some of the major topics covered in here, we are going to be using AWS infrastructure for almost everything we learn here. The previous iteration of this course used to use the on-prem infrastructure at Boise State with Hadoop and MapReduce and HDFS. So starting this semester, we've cut out like 4 weeks of what previously used to be in the course. So we have a lot of free time to work with that is currently not filled with anything. So if you have stuff you want to talk about, bring it up and we can go through it. Any questions so far? All right. Also, there isn't really a textbook for this course. There is an O'Reilly Learning Spark book that you can use just as an optional reference. There are also plenty of online resources you can use to find information on how to do various things, and we'll cover all of that here too. Yeah. Are you experience and how you use. So we're gonna go through how to use everything from the ground up. And so if where do I hide this thing? So if you have a question or need help with anything and it's outside of normal operating hours or whatever, you can go to Canvas and post something on a discussion board. And these discussion boards can be anonymous, so you can post with your name or not, and either other students can answer your question or I can answer your question. And we used to use Piazza for this purpose, but Canvas has it right here, so we're going to try using this. Questions about that? All right. All right, so for the homework and the programming projects, the majority of the work in this class is going to be individual. Most of the assignments will be programming assignments. And so I want this course to be heavily application focused. My, experience comes from my industry work, and I want the work we do here to reflect that. So most of the assessments are going to be project based. And this is how the grading is going to break down. We've got 1,000 points total in the semester. 65% of those points go to projects and homework, and 35% of those points go to exams. And in the grades, as in how I assign letter grades at the end of the semester. I'm not really going to do the plus or minus system because that never helps anyone. And everything is standard beyond that. It's, between 900 and 1,000 is an A, 890 is a B, 700 and 800 is a C, and so on. If you need to submit something late because you have stuff going on outside of this class that's interfering with it, that's fine. You have a budget of what we're going to call 6 late day coupons, which is you can allocate them almost however you want over the course of the semester, and they're meant to give you some flexibility in when you can submit your assignments. And so these kind of late day coupons are not they're not really divisible by hours or anything. So if you submit your assignment a few hours late, it does count as using one late day coupon. So you might as well take advantage of using the whole day if you need the extra time to kind of patch things up and tighten the screws. And I prefer to give as quick feedback as I possibly can. So, and in order to do that, I need everybody to submit their assignments and then I can release the grades. So in order to do that, I'm going to limit you to using 2 late day coupons maximum per assignment. And, as always, there are exceptions to everything. So if you have something going on and you have some circumstances that are restricting you from finishing your work, come talk to me and we can work something out. Right. And of course, if you have any other difficulties, I'm right here and you can come talk to me. You can also talk to the CS administration if you need anything. Let's see. Lastly, academic honesty policy. Please don't use other people's work. It's not going to be a good time if I find you doing that. And the purpose of, being here is to learn things. And if you're using someone else's work, you're not doing that. And so if you're having trouble with the work and you're having a hard time getting it done, I am available as a resource for you. So please talk to me. Because I've had students that have submitted assignments that are clearly plagiarized without coming and asking me for help first. That was not good. So if you're having trouble with an assignment, please come talk to me and I will give you as much help as you need. All right. Okay. That's all. Any questions about the syllabus? You talked about office hours, but the office location is down here. No. So I'm an adjunct, so I don't have an office here. There's no class after us, so we might just be able to stay in here, but if we get booted out for whatever reason, we can go to the tutoring lab or go upstairs or anything like that. So office hours are just right after class every day. Any other questions? All right, let's get into it. Okay. So, as I said before, my name is Arjun Shukla. I got my master's degree in CS from Boise State in 2021, and I've been working at Count ever since then. I wasn't always a machine learning engineer for Count. During my first year, I was like a normal web developer. That's not what I am now. So, Count is a software company that deals with e-commerce fraud and fraud control. So our company and what our job is when somebody submits an online transaction using a credit card, those online merchants, say like Walmart or somebody, will send the transaction information to us and we will tell them whether or not the credit card transaction is fraudulent. And then return a response in real time so that Walmart can process the rest of their payment. And in order to do this, we have all of this data science and AI infrastructure around making sure that our customers can use their decision. And so in order to manage that, we have a bunch of data pipelines we need because we get about 5 million transactions per day, and that builds up really fast. That equates to, over 1 billion transactions every year. And so we have a very, very fast growing data set, and that requires our data pipelines to be constantly maintained and reiterated upon so we can make updates to it. In addition to that, I also do normal software engineer things. So I have to write web services, and our web services run on Kubernetes. And in addition to those other things, I am maybe alone among the machine learning engineers that count, in that I also do quite a bit of research work there too. So we have consumer identity products, and that I have done research for, and these identity products will basically tell, one of our customers whether or not their users are using someone else's information. And so I have done research for Count's identity products, and that research has been put into production and made part of our products to serve to customers. And so I've at Count been part of that whole data science process. You can initiate the research and ask your initial questions. You can build your prototype. You can kind of solidify that prototype into something resembling a product and sell it. And then you have other consumers who are, it's basically an API web service now. And so based on the work that I and other data scientists at my company have done. Questions about that? Yeah.
So you didn't just take to the fraud transaction. So what type of data you have taken the one and all the other the companies, like is it all the data information or the items like product item?
It's a lot of different stuff. So we contain, we take the credit card information. We don't actually know what the credit card number is when we take it in. We have our customers encrypt it first. But we have kind of a hashed credit card number, and we take that. We have the billing information, so the name of the person who is listed with the credit card and what their address is. We also have their email address and their phone number. We have shopping cart information, so we know what they bought. We know what currency they used and how much every item in their cart costs. We know how much of every item they bought. What else?
Additional person would like, for example, so you were taking the user of the shopping cart. So do you have the history of the just specifically very previous purchase history or something like this?
Well, it's more complicated than that. So what we do have is every customer we have sends us like a user ID. So if a user creates an account, that account is given some sort of identifier in whatever system they use. So when you create an account on Walmart.com in order to buy something, then in their database somewhere, that's given an identifier so they can tie your request together and build a profile and such and such. We do have that information, but that's where things get very difficult, because if you use completely new information and shop at the same merchant online, a lot of the time it's very hard to tell that you are the same person. We can't just assume that just because somebody may have the same name that they're not the same person, just because it's, listed as a billing address that we've seen before. We can't assume that these people are related or living together. And just because you use the same credit card number does not mean that it's the same person or even related people, because sometimes credit card numbers can be reused. So we can't trust that. So a lot of the challenges that we have to deal with are dealing with terrible data quality. And that's part of what makes detecting fraud really hard, because we have this problem where if our customers keep sending us data and some of that data is, fraudulent transactions and some of it isn't, the better we get at detecting fraud and denying those transactions, the less fraud data we get. So there's this survivorship bias where we have, 99% of the transactions are not fraud and they're good and they go through. 1% of the transactions are fraud and they go through. We get really good at detecting those, but then, fraud patterns change all the time. And so we're always working with data that's a little bit outdated. And the better we get at detecting fraud, the less fraud we get. Because if you decline a transaction and the transaction never happens, you'll never get confirmation on whether it was fraud or not. So our signal is fundamentally flawed in that way because we're dealing with transactions that are coming in real time. Any more questions? Okay. So as I said earlier, I work with big data on an almost daily basis, and um, I'm also a little bit alone on because the other MLEs or machine learning engineers on my team don't work with big data as much as I do. They work more with the real-time services and things like that. So I'm a little bit further back in the back end, and I manage quite a few data pipelines. But in doing so, I'm also kind of a mix. So I do both science work and also engineering work. And over there, we have this kind of separation between science and engineering. And there are key differences because on my team, we have machine learning engineers that are there to take the prototypes that are built by data scientists and put them into production so customers actually use them. So customers are able to actually use them. And that is a completely different job from what the data scientists are doing, which is they're looking at our data, they're trying to build intuition about it, they're trying to figure out what the right questions to ask and how to answer those questions. And a lot of the time, their exploration is very ad hoc. So they don't really know what they're going to look at in advance. And if they're going to write code to explore some aspect of the data, they might never use that code again. It's totally different from a normal software engineer. When you write the code, you check it into whatever source control your company uses, and then it's just there. And it stays there, and customers use it unless there's a bug or something, or the software gets decommissioned. And so a lot of the code that you will write as a scientist is very ad hoc and it's short term. And so a lot of the time, the scientists do not have the same maintenance standards for their code that the engineers do. And that makes our jobs slightly more difficult. But that's part of the job. And so I would say that scientists make more extensive use of big data tools than the engineers do because they have to work with these kinds of things all the time. The engineers, at least the ones who build data pipelines, will also do this fairly regularly. But, at count alone, there are probably 50 engineers. And I think I'm the only one there who regularly deals with big data tools like this. So at least from an engineering standpoint, knowing how to do all this puts you in a more specialized role. It's still useful for engineers because it improves your repertoire. And if you're primarily an engineer versus primarily a scientist, this class is still going to be very useful for you. But if you are planning to go into data scientist, this class will definitely be useful for you. Yeah.
So you were talking about whether the next 2 weeks or whatever time. It would be really, really great to know kind of best practices from a data science point of view, from a coding point of view, to help if you were talking about how you don't have to worry about as much rerunning.
Yes.
It would be good to know kind of what you could do to make this an easier position. Because I'm writing it anyway. I'm not just going to write it in a way it's going to put that in.
Yes. And so this is kind of weird for me because I'm involved in both parts of these processes. I have built prototypes for engineers to productionize, and I have also productionized prototypes built by scientists. And there was one piece of our identity product where I kind of did both of those things, where we have certain identities, but it turns out we had, the same person that existed in our database twice. So what I was trying to do was figure out a way to detect that and to merge them together. And I did the research for that part. My boss told me I wasn't also allowed to productionize it, but because I'm an engineer, I wrote the code that I gave to the engineer for the prototype in such a way where it could kind of just be plopped into the code base. I don't know how easy that would be to do for other data scientists because I am also the one who manages that code base. So I know exactly where everything goes. But I would say more generally, the things that your IDE would warn you about are the things that you need to watch out for, which sounds pretty basic, but the data scientists use, have you all used Jupyter notebooks before? Yeah. Okay. So we got good Jupyter experience around here. Yeah. A lot of the scientists use Jupyter. I love Jupyter notebooks. They're, great for prototyping and they allow things to be interactive, but it also makes organizing the code a royal pain because you can execute the cells in any order. And if you don't make sure at the end of the day that when your code executes, all of it does so correctly because you're not relying on some context that was available when the code was running, that you didn't delete some sort of cell somewhere, that you didn't rearrange the cells in such a way that if you run them in order, it doesn't work anymore. So we have to deal with all that. But it's fine. It's good. And so having worked on kind of both sides of that, honestly, the advice I would normally give is I've seen a lot of unused variable issues where some data scientists will be experimenting with, maybe putting different features into their AI model or experimenting with different criteria to classify things. And they'll calculate a bunch of different features that they were thinking of maybe using in their prototype. And then they discovered those features didn't work. And so they didn't use them in the version that they give to us. But all of those calculations are still there, even though they're not doing anything. And so when, I'm productionizing code and I'm going through a notebook to see what I need to migrate over, I cut out a lot of stuff. And so that's going to be, part of like the code quality guidelines that I'm going to give you all during our programming assignments is, it's really good to experiment with a lot of different things, but when you submit the assignment, clean it up, streamline it to make it easier for me to grade, and also to whatever engineer is going to put your prototype into production. Or if you're putting your own prototype into production, you will have to do that yourself too. And so when you're managing a crap load of code that exists in one notebook, organization is challenging, especially when it comes to code that is difficult to reproduce. It works on my machine is a huge problem. That meme has a lot of truth to it. Any more questions? All right. So I want to define big data. So what we're going to do is I want everybody to split off into pairs or groups of three, and I want you to kind of discuss with each other, how would you define big data? Where would you draw that line? So if you were looking at a data set and you had to decide whether or not this qualifies as big data, how would you do it? You can look through it through a bunch of different angles. Is it just like a specific amount? Is it a gigabyte/terabyte cutoff? Is there some other condition that needs to be fulfilled in order for it to make it big data? Is there some kind of combination of the two? And this is an extremely opinion-based question. So there are no wrong answers, but I do want to hear thoughts. Go. We can take about 5 minutes or so.
Yeah.
Then that like in spreadsheet plans, like once you did 100 cells. Oh my God. One there's like frequent number. You have to have. Not something that was like. Something on. Of course, I want.
Right. Yeah. It's like, I mean, but I think that lots of. Kind of what are so many are science and
Like multiple words.
yeah.
But it's not a. And there's different, like, very popular.
Yes. Whatever. That's like that.
Like, that. That's. And what, now.
Yeah.
It's just, now. You know, higher quality. You don't have to do this to the fast. If I have a phone bill, that's the same size now as what these one D memories.
All right, is everybody ready? Let's see what we got here. You three, what do you think?
So yeah, so as we, if we know that there isn't any single right answer or wrong answer, we just randomly discuss and some of it. We just sort of like how much storage it can take to store the data, or like if you can see the all the data all at once, we can do it like it's not together, and it isn't like it's not together. For example, if you want to keep your memory or like don't do anything all at once, you then have provided the resources. So yeah, that's how we can see how to better we can
Okay, that's an interesting definition. Let's write that down. It fits in memory. Is that a good Is that a good summary? Is there something else?
And all the class, like, you can go to the data,
Yeah,
all the
Yeah.
like, you know, like, yeah.
yeah. Okay. It all fits in memory. Okay. What about 2, 3 in the back over there?
That's fine. So you go, you know, if you think it's really good, recommend that between them. So if you are anything about setting up like the that you should pay one money, or having an action and such an like having post probably the action, you can possibly do. We can do it from structure, calculating, to be
Yeah, so it very much what constitutes big data very much depends on the type of data you're working with and what you're trying to do with it. Did you did you come up with a bit stricter um a bit stricter classification for it? Yeah, that's all right. No, that's fine. You too?
Okay. We actually also talked about it all the, basically we can fit it all on one machine and run it all. The required for the putting my green, then it would be good.
Okay.
So that's machine specific, but we also talked about not only your current data requirements, but if it's also going to grow to a size from that sample data, then you would put it each of the good. So if you anticipate, even if you only have, the people like right now, but you would just really go with it quickly, you should turn out to price it and everything. You would down to zero.
Okay. So the 600 machine. And there's this other corollary question of is it scale? So does it scale to only one machine? Or yeah. Okay. What about you two over here?
It should have the detailed version of the we are working on that. Not having the detailed version, it will be considered a lot of detail or something. Having a very less amount of data can get visual into not having a perfect model or something like that. Right. Suppose we have very less amount of data, and obviously it will not be the accurate or something of perfect model that we need. But having a big data and big detail of big data work and that specific whatever we are working on that. I think they don't do it with my data.
Okay, so you're discussing more on like on the data quality side, on how is this data useful and how can we extract insights from it and how can we extract features from it.
Or like knowledge of anything like when it obviously data is now for any product, we need to have a data, right? So how that is going to be useful for that thing, like having a big data and not having like having small data, how it will affect the quality of the product.
Yeah, we have to deal with that a lot at Count too. Um, because in addition to the survivorship bias I mentioned earlier, our fraud signal itself is also terrible. Like when we have a particular transaction that comes in, and let's say that transaction was fraudulent, a lot has to happen for us to actually know that transaction was fraudulent, right? So the person whose credit card it was has to go look through the transaction history, notice a transaction, know it's fraudulent, and file a fraud claim. Then the bank has to talk to whoever was selling the product online and tell them, hey, this was a fraudulent transaction, so you need to reimburse the cardholder, because that's how it works in e-commerce. An online merchant has to be the one to reimburse the cardholder and not the credit card company, which is an interesting difference between how it works in in-person transactions. If the transaction happens at like a brick and mortar store and you swipe your card physically and somebody else swipes your card, then the credit card company has to reimburse you. So that's a key difference between, what we handle in online transactions versus what the credit card companies handle with in-person transactions. That's honestly what created our entire business model. Because if there are way, way fewer credit card companies than there are online stores. And so that has completely changed the way, our company does business online, is because of that rule. And so in addition to that whole interaction having to happen between the fraudster, or the person who's buying the credit card or buying the stuff online with the credit card, the person who actually owns the credit card, the merchant who's selling the stuff, and the bank who manages the credit card, all the information has to actually get reported to us, which sometimes doesn't happen. So the chargeback might happen and the original cardholder might get reimbursed, but we might not actually know about it. So we have a lot of transactions in our data that are fraud, but we have no idea that they're fraud. And we kind of have to assume that they're not fraud because most transactions are not fraud. So we have a lot of fraud in our data that we don't recognize, and that causes data quality issues. And not only that, but when we train AI models, to recognize certain fraud patterns, the vast majority of the stuff in our data is not useful. And so we have to do a lot of work to clean all that cruft out. And because a lot of our data is, like text-based and things like that, so we have emails, right? If you look at an email, you can be reasonably sure just by looking at it whether or not it's a real email. Like when you look at an email and you just look at the username in the email, it should be pretty easy to tell whether or not a real person uses that email or if it's generated by some script somewhere and it's a random assortment of letters and numbers. That's easy for humans to do, and that's hard for machines to do. And it's even harder to train an AI model that does that, because when it comes to fake emails versus real emails, we don't actually have any data. We don't have a data set full of stuff that's like, this is a real email, this is not a real email, and such. That's a problem too. And we have other fraud patterns that come from somebody hacking into your account. And so all the information looks real in the sense that it is actually your data. It's just being used by someone else. And so there are all these fraud patterns that we have to capture, and all of them exhibit different characteristics. And last group, you all think. Well, yeah. So a lot of the time we will have to do quite a bit of data munging and feature engineering before those kinds of things are actually useful. Like for the email address example, right? When you just provide an email address, most models don't know how to deal with that. You can maybe do something with NLP, but in real time, you could do NLP on an email, but a lot of the time NLP is expensive to run and it's expensive to host, and your company may not have the resources to do that, or the constraints might be too tight. I mean, if you look at ChatGPT and you look at how long it takes to respond, sometimes it's a few seconds. And in our sphere, that's unacceptable to us. our SLA, our service level agreement, as in our expected response time, is 1/4 of a second. So we have to have our requests come in, we have to do all of our analysis, we have to predict on the AI model, we have to store everything in the database and retrieve all the statistics and all of that stuff within 1/4 of a second, 99% of the time. And so there are a lot of AI models that will not support that kind of low latency requirement. Okay. And so the definition of big data that we're going to use in this class, and great responses, by the way, that generated a lot of discussion. That's what we're going to try and do in most of the semester. This is going to be a largely discussion and activity-based class. I have, for the most part, we're going to do like a lot of live coding exercises and work through things. So it's going to be fun. So the definition of big data that we're going to use in this semester is if it's too big for one machine, then it's big data. And the reason we're going to do it this way, and the reason we're defining it this way, is because the nature of the analysis and the types of algorithms that are available to you, those all fundamentally change when you scale past a single machine. It fundamentally changes. It changes the way you program. It changes the way you have to think about the problem. And that's a big leap to make because a lot of the time, with these larger machines, you can't just write a for loop because the code is running on 100 different machines. That's what we do in our identity data pipeline right now that I built, is we have 100 different machines, 6 terabytes of memory, 1,000 cores, and they're all communicating with each other and exchanging data in order to complete that task. And so that is a big change in how we program from just doing things on a single machine. It also matters what kind of analysis you're doing too. So, maybe you're trying to train a machine learning model, or maybe you're just trying to aggregate on keys and get statistics. Like, you're looking through the transactions and trying to figure out, okay, how many transactions does this email appear? You want to do that for every email. It's a lot easier than, say, like training a random forest or decision tree on a bunch of transactions. It's a much simpler process. And so what qualifies as, big data will change because the nature of the analysis and what we're trying to figure out will also change. So just gathering statistics on emails is a lot simpler than, training a decision tree. And it takes much longer to train a decision tree on 1 billion rows than it will to take an aggregate statistic on 1 billion rows. And so that's part of the classification here. Another part is a lot of the time when we say, it fits on one machine, we can do it on one machine. We might be able to do it on one machine and have it take like a week. And sometimes that's fine. But then also, if we need the results very quickly, that might not work. So again, in our identity pipeline, we run through it every month. It's a global algorithm, so we need to rerun the entire thing on the entire data set every single month. And so that runs in about 12 hours. And theoretically, you could use, a smaller cluster with fewer resources and kind of drag that out, but ain't nobody got time for that. That just won't work. Because if something goes wrong in that process, we need to be able to update things quickly and be able to troubleshoot quickly. And another thing we're going to talk about is how hardware scales and how the difficulty and the complexity of computing things on certain data sets will change as you scale things up. Because a lot of the time, if you have a certain data set and you think it's going too slow, so you double the size of the cluster, you might actually get better than double the performance. And that's because of, hardware details that we'll talk about later. But there are like these different tiers of storage on certain machines. You have off machine, which is you have to access it over the network. It's local, but it's on an SSD somewhere, or if it's in memory. And so all of those things have different performance profiles associated with them. And if you can fit your data into certain categories, then a lot of your analysis would be much faster. And so that can happen in the sense that, if you double your resources and you double the size of the cluster, you might actually be able to finish in a quarter of the time. And so that is a much more efficient use of resources because the cost will usually scale linearly. So as in, if you use a particular cluster of a particular size, let's say, let's take the identity cluster that we use at Count, for example. It uses 128 machines and it's running for 12 hours. And so that 128 machines costs about $60 an hour to run. And so if we double the size, that would cost $120 an hour to run. But in certain circumstances, we might get better than double performance. The reverse is also true in that just because you're doubling your resources doesn't actually mean you'll experience maybe any improvement in performance at all. And that could be due to the nature of your analysis or the nature of your data and maybe certain keys that you're aggregating on. And we'll talk about that too. And so one of the reasons this is so complicated is because these machines have to coordinate with each other and exchange data with each other all the time. And because they have to do that, that means that because this data is split between a bunch of different machines, they don't have access to all the data at the same time on every machine. And so if one machine in the cluster is analyzing the data and it needs access to a piece of data that some other machine has, then they have to ask for it. And so there are only certain kinds of operations you can do in these big data distributed systems. And we're going to talk about how to use those operations and combine them together in ways that allow you to do a huge array of different things. Because this giant identity pipeline that we have at Count, it's hundreds of lines of code, written in Python, almost exclusively using Spark, and it does, things like graph analysis. It will aggregate different statistics on a bunch of different things, and it will combine everything together. And so there aren't very many operations that you can do. There are very many different kinds of operations you can do in a system like this, but you can combine them together and they're composable in a way where you can make a lot of different things. So it's deceptively powerful in the sense that there aren't very many operations, but they can be combined in ways to produce a huge variety of different programs that you can write. So these systems are very powerful, but they also have limitations in the sense that there are things you just can't do with them. And we're going to talk about that later in the semester too, where not only have I had to use big data systems like this, I had to scale down and write code that ran only on one machine and figure out how to do that. Because the types of operations I was doing, there was no way to express them in a distributed system. So I had to figure out how to make it work on one machine. Yeah. Yes. So how the data is stored will very much affect, how different things are, what is calculable and what's not. And a great example of that is kind of the distinction between, we'll talk about this later too, is the distinction between a data warehouse versus a database. And the purpose of a data warehouse and the purpose of a database are very different, and the performance profiles and what they're supposed to be doing are very different. And have you all used SQL before? SQL? Okay. And there are certain things that you can do in SQL databases like Postgres or MySQL or Oracle. And there are things you can do in SQL data warehouses like Snowflake or Redshift or any of these other things, or Hive. And if you're used to real-time systems like Postgres or MySQL, and you go to data warehouses, there are just certain things that you have to unlearn because there are things that you can do in databases that are not possible in data warehouses because they're meant to do different things. Any other questions?
Can you write something? Do you know before you run it, like how many machines you should run it on?
Not always. If I've done something similar in the past, I'll usually just compare the two and I can make a good guess. Um, but if I'm in uncharted territory and I need to do something that I've never done before, no. And so that's what, and in a lot of these cases, it's really hard to determine exactly what you need to do in order to get the thing to run. Because one of the biggest challenges in working with systems like this is that they are not observable. They are not very observable in the sense that when you start running the code and it's running for like 2 hours because it's going through 5 billion rows, and then it dies an hour and a half in and it says, oops, I ran out of memory. It's not going to tell you why. So you kind of have to look through the logs and make a guess as to what's going on, and then try it again. And then you have to wait for an hour and a half, and then it dies again. And it says, oops, I ran out of memory. And it still doesn't tell you why. And so kind of an essential part in learning how to use these systems is if you can understand the fundamentals of how they work, even on an abstract level, and you know what they're doing, then you can probably get a good idea of why it's failing. And so a lot of the software engineering tools that you use, like debuggers or even print statements, you can't use here. Debugging programs written in these distributed systems can be an absolute pain. And so a lot of the time, fixing these problems is literally just guess and check. You have to think through where the data is going and how it's getting there and what's happening to the data once it gets to its destination. And if you think about it hard enough, you might guess right. And you'd have to come up with a solution that assumes that's what the problem is and then try again. That's been my development process for the past 3 years. And sometimes there are systems that try to be smart and then fail. So we use a data warehouse system called Snowflake at Count. This is a really funny story. And what happened with Snowflake is we tried to do an aggregation, and this was the biggest aggregation we've ever done. Like we had 700 million different unique keys that we were aggregating on, and we were calculating like 100 different statistics on every single key. So Snowflake has these compute resources called warehouses, and warehouses are just clusters of machines of a particular size. So the smallest warehouse has 1 machine, the second smallest has 2, and every time you go up a warehouse size, the size of the warehouse doubles. And so the largest warehouse they have is 128 machines, and that costs $430 an hour to run. It's expensive. And so what happened is one of our data scientists needed to run this aggregation query, and he left for the weekend. And so he comes back 72 hours later, and it's still running after having ran out of memory like 3 times and then retrying it. And they charged us for all of it. We got a refund. We got a refund because we were like, okay, if you run out of memory and you keep retrying, we can't be held responsible for that. So we got out of like a $12,000 bill from Snowflake, which was good. But yeah, $400 an hour to run, and it wound up just breaking and breaking and breaking, and it kept retrying, but its resources still weren't enough. So that happened. Um, there were two solutions to that problem. The first one is we split the query to aggregate. So one query aggregated like a fifth of the features, and then another query aggregated the next fifth, and then another query aggregated the next fifth. So we had 5 queries like that. And then when we were done, we joined all the results together into the same table. Because the aggregation itself takes up a lot more memory than the results. So we were able to fix the problem that way. I re-implemented those aggregations in Spark in such a way where we could do them all at once, but I had to do something a little weird and custom with the aggregations. And we will talk about what I did later. Because sometimes you have to do that. And there's other weird crap that I've had to do too. Like there was this one time I was joining like 6 different tables together in a chain, and it broke, saying, oops, I ran out of memory. I can't join these 6 tables together. And I'm like, that's BS. You have enough memory. What are you talking about? And then I eventually figured out that the tables I was joining the largest one first. And so when you join the largest one first, the system that's responsible for actually executing the join isn't smart enough to figure out that I was joining on the same key on every join. So what was happening was it was taking the largest data set and sending it to all the machines, and then that's one join done, and then it joins them all and it kind of concatenates them all together again and sends it again, and then it sends it again, and then it sends it again, and then the garbage collector couldn't keep up on the cluster. And so it was allocating the memory every time it did another join in that chain, but it wasn't freeing it properly. And so just by changing the order of the joins, you take that first one and make it the last one, so it doesn't join as many times, that fixed the problem. There's all kinds of weird things like that that you will not figure out unless you know how the system is exchanging its data. And that's the kind of thing we're going to learn here. Sound good? All right. So we're going to use AWS in this course, but we don't have enough time to go over it right now. So what I'm going to do is, well, first of all, I don't know any of your names. So I'm going to take a video and I want everybody to say what their name is, and I will have them memorized by Thursday. Sound good? Okay. So we can start with you and move on. Hold up. It's not ready yet. All right, shooting.
First, me?
Yes.
Yeah, okay, go.
Yeah. That's me. That's me. Just me.
Sure. All right. Sweet. Okay. So the other thing we're gonna do before we adjourn for the day is I have a background check survey for you. So I want to see where everyone's at because we're kind of doing things a little bit more ad hoc this semester because we have so much free time. And because we're working with completely new infrastructure we've never worked with before. So this is also the first semester that we're doing things with AWS and things like that. So I have a bunch of questions for you guys on where you stand with everything. So we can just take the last 15 minutes and have you guys do the quiz. And it is not quiz. It is a graded survey in the sense that it is worth an amount of points, but there are no wrong answers. So as long as you answer the question, you'll get the points. And that should be in Canvas. Does everyone have access to Canvas? Okay. And so I kind of allocated the last 10 minutes so that y'all can do the survey. Huh? No. Yeah.
In this subject, the primary subject or something like that?
In what subject?
Okay. This will.
Well, yeah, so there will be programming projects.
Assignment will go around.
No, so there will be multiple projects, including a final project. Yes.
I'm looking at exam, like, how would they be more in individual things about the coding thing or in next stuff right now.
I'm more of a free answer person. I like to hear people's thoughts. So they will be mostly free response questions.